Hello, welcome to the Institute, in which we're going to go over this little sample MegaWork energy problem. So a couple of key things that we have is we know the mass of the block is 5 kilograms. It's at the top of this ice ramp. It's 20 meters above point B. So in other words, from here down to here, this distance, I'm going to move this out of the way for me. This distance is 20 meters. And it says it's 15 meters above point C and D. So if I was to cut this over like that, then from here down to there would be 15 meters. Now I don't know if we'll need it, but just kind of carry this over. That means that this would be 5 meters, just in case we need that. So that's all information, and then we're going to launch the block at 1 meter per second. So it's going to start off with a little initial velocity of 1 meter per second. And basically all of this is frictionless. So from A to B to C, I'm going to put that the mu is equal to 0. There's no friction. Then when it hits C, all of a sudden it does run into friction. So during this part, we have mu equal to 0.75. Now I'm actually going to put a little k on here because it's actually kinetic friction that we would be dealing with. But the rest of the ice ramp, it says, is frictionless. So we're going to find out two things. We're going to try to figure out how fast it's going down here. So we're going to find its velocity. And we're going to figure out how far it slides between C and D. In other words, how far is it from C over to D. And that's our idea. So this is a great one to kind of apply the MegaWork energy. So as we start out, the first thing I'm going to always suggest is write out the full equation. So we've got work equaling change in kinetic energy plus a change in gravitational potential energy plus a change in elastic potential energy. Now, since there's no springs or elastic materials, we can get rid of this one. That's just going to disappear. Now, in part A, we're going from point A to point B. We're coming along this frictionless track. So when I think about work has to be some external force that's acting on it. Now, I know that gravity is an external force, but gravity is going to be in this. And basically, our change in GPE means that we have a change in height, which we do. We're going to go from A down to B. So we're changing our height. So we do have this. We do have a change in gravitational. We're changing our kinetic energy if we change our speed. I'm guessing that it's probably going to be going faster at point B than at point A. So I do expect there to be a change. The weird one is work. Since it's on a frictionless surface and gravity is already taken into account with GPE, work would have to be other forces, and that would most likely be friction. So in this case, we don't actually have any work. So we took this from the MegaWork to the mini energy because we have 0 equal, and then for our change in kinetic energy, it's 1/2 mass times my final velocity squared minus 1/2 mass times my initial velocity squared. And then over here, for my gravitational potential energy, it's going to be mg times my final height minus mg times my initial height. First thing I notice, which is really kind of cool, is everything is multiplied by m. So I could actually divide by m on both sides. So the mass of the block is actually irrelevant for this problem, which is kind of neat. The next thing is heights. Heights, you have to pick some kind of reference point to actually work with. I would probably make point B be my reference point. So I would make this a height of 0 so that this 20 meters would actually be the initial height. So this would be the final height and this would be the initial because we're going to go from A, which is 20 meters up, down to B, which is 0. So that allows us to actually eliminate this part as well. So now what I got is 0 equals 1/2 VF squared. I don't know what VF is. Minus, I'm going to put my numbers in. 1/2, my initial is 1. And then here I've got plus 0 minus this. So I'm just going to have minus 9.8 times my initial height of 20. Then it's just a math problem. So I'm going to basically, this is going to end up being 0.5 and this is going to be 196. So I can combine those together and then bring them to the other side. So I have 196.5 equals 1/2 VF squared. I would multiply by 2 on both sides. So this can make this 393 equals VF squared. Square root and you get VF is 19.8 meters per second. Bam. You just did a MegaWork energy problem. It's that simple. So it looks very daunting with an equation, but we should be able to simplify it and kind of work it out. Part B is going to work the same way. So we're going to start off with the MegaWork. Just write all the pieces again. Now I can probably not even write this part because again there's still no elastic material, so we don't have to worry about it. The work is going to be a little bit different. So I know during all of this part we're frictionless, but your initial position can be whatever you want. So we can start at A, we can start at B, we can start at C. Most people, when they look at this problem, part B, they think they should start at C and go to D, and so basically move between there. The problem is, I know where this is in terms of like a height, but I don't know what its velocity is. So since I don't know that velocity, I probably would not start at C. Instead, I'm going to start all the way back here at A. And I know that seems weird. You're like, why would you do that? Because I know everything about it at A. I know its mass, I know its velocity, and all of this, we're going to have no work being done. It's only going to happen when we get to C, and then we get work. So our work is actually going to be done by friction. So our equation is minus mu k, so there's the kinetic friction, and then it would be times the normal force, but since it's on a flat surface, the normal force just equals the weight, and then multiplied by the displacement. So this displacement is what we're going to go after there. The minus sign is there because friction is always going to act in the opposite direction to the motion. So if the block was sitting right here, it's moving this way, but friction is going to act in that direction. So their angle is 180 degrees. Cosine of 180 degrees is -1. Then over here for my kinetic energy, my final is actually going to be 0. So we're going to finish with a final velocity of 0, and we start with 1 meter per second. So all I'm going to write is this part of the equation. I won't even write that part. So I've got 0 minus 1/2 m times vi squared. Yeah, that's kind of nice. Negative, negative. And then over here for my gravitational potential energy, again, I get to pick whatever I want for my reference point. I would probably make CD be my reference point. So I'd actually make this be a height of 0 for this part. And so the initial height would be this 15, and this could be my final. So I can still have a final equal to 0, and so what that does is up here I get to still cross this out like I did before, and I only have that part. So I have minus mg times the initial height. If you notice, everything's subtracted, so I can take all these negative signs and turn them into positive signs. And then if you also notice, we have mass times everything. I can actually cancel out all the masses, which is kind of neat. It basically means that when you don't have elastic materials, you can often cancel out the mass of the object. Then we're just trying to solve for D. So I'll put in my mu k, which is 0.75, plug in gravity, 9.8, D. And then over here I have 1/2 times this 1 squared, so that's just going to be 1/2 again. And then plus, I have 9.8 times 15. So that's going to be 147, I think. Yep. So these together is 147.5, and then we can multiply that. 0.75 times 9.8. is 7.35, so this is 7.35 D equals 147.5, divide by that 7.35, and that should give me what D is. And when I do this, boom, 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 you get 20. So this thing would slide to a stop over 20 meters, which is kind of neat. So it's kind of interesting that this came out to be just a little bit less than 20, and that's exactly 20. So it's just kind of random that it came out that way. It doesn't always come out that way. So I hope you liked this problem for the sample MegaWork. Thanks for joining.